Right. Good evening. This is week one, Thursday, and today's lecture will go from now to 9 o'clock. We take a break at about 8 or 8:15. Okay. So I'm going to continue on the introduction example, and why I'm doing this introduction example is to highlight to you at the end of this course what are the expectations, okay, what you should be capable of, okay, so you can see the overall scope of the course. And then after that, we're going to start on a new topic. I hope to start on centric buckling. Okay. Regarding the homework, I will post the homework hopefully tomorrow morning. And the homework, I will give you at least 7 days to complete the homework, at least. Okay. Right. So let's recap this example. So this example, we have a overhanging beam. On this overhanging beam, you can see there's a gradient distributed load. And it specified to us, or the question specified that we are going to calculate the factor of safety at point B. Okay. So if you look at the lecture on Tuesday, a question like this has a lot of layers of knowledge required, like how is the yield strength determined and how are we going to calculate the factor of safety. Ultimately, for this question, okay, is to determine omega naught and the factor of safety. Okay, so as I mentioned on Tuesday, and on a beam like this, so what you see over here is a cross-section view. And I did mention that failure will occur at this point that I'm drawing now. Okay, so this is failure point. So on the failure point, we put an element. Okay, we place an element over here, which you guys had last week, or we call it element alpha. Okay, so we put an element or failure point, and this is the location of element alpha. Okay, element alpha. We deliberately put it over there because over here failure will occur if fracture were to occur in this structure. Fracture will either occur here or occur here. Okay, and that's the only reason why we put our element there. Then we constructed 3D mold circle. Okay, so we constructed 3D mold circle based on this element over here. And on the 3D mold circle, right, you can see we have three circles. Does not mean 3D mold circle is a sphere. No, no, no. 3D mold circle over here is the element is in 3D, but we have to construct three circles on mold circle domain. Okay. So now what we have to do is what we are given. Okay, what we are given is we were given that the material, okay, the material has a stress yield, and the stress yield is equal to 200 times 10 to the power 6 Pascal. Okay, and this yield strength, right, is measured in uni-axial configuration. So I did mention also this value over here is a principal stress. And what do I mean by principal stress? Is where the shear stress is equal to 0. Okay, so if you go back to our lecture last week, okay, our not last week, on Tuesday, right? This is the mold circle from experimental. You know what? I'm going to copy and I'm going to paste over there so you have it also. Okay, so this mold circle over here is from experimental work. Okay. So now we are going to apply the maximum shear stress criteria. So if you look back at this question, we are going to apply the maximum shear stress criteria. So what do I mean by maximum shear stress criteria? So this will be taught in week 10 or week 11. So I'm going to write this down on maximum shear stress criteria. So there are two key features about this criteria. Okay, so what they are. So number one, okay, there are two key features. So number one is tau max, okay, will be equal to stress yield divided by 2. This is the first one. The second thing that the maximum shear stress criteria specify is the stress in yield is equal to the same stress in yield, okay, in minus. So i.e. the yield stress in tensile is also the same as the yield stress in compression. Okay, so that is what this criteria is. Okay, so another words, you realize that this maximum shear stress criteria, another name we call it is known as Tresca. Okay, so just to introduce to you the name first. So it's a Tresca criteria. I deliberately put it tau over here. By right, Tresca is spelled T-R-E-S-C-A. And if I put a T in and put a tail, okay, so you know that it is shear. Something easy for you to remember. Okay. So from here, now we have to work based on the mole circle now. Okay, we have to work based on the mole circle. So what we are going to do now, okay, I'm going to get the mole circle. I'll tell you what we're trying to achieve down here. Okay, I'll copy the mole circle again. And I think I'll go to a new page. And I'm also going to get the element across. So we construct the 3D mole circle from the element that I've just pasted over there. Okay. So now, what are we trying to achieve down here? So we have to make sure, first of all, we have to ensure that we have to determine omega, okay, such that, okay, we have to determine omega such that, okay, such that two conditions has to be satisfied. Okay, such that tau max has to be less than 100 megapascal. Okay, and then the stress mean must be greater than minus 200 megapascal. Okay, we have to ensure that. If it's not, okay, our omega value is wrong. Okay, so now, in order to do this, right? So now what we're going to do is we're going to look at the 3D mole circle now, and now we have to determine. Okay, we have to determine what is our tau max from mole circle. Okay, so I'm going to go into the graph mode again. Right, so we know, oh, I did not paste the graph properly, my bad. Hold on, pardon me. not want to move. Okay, so we are going to determine tau max from mole circle. So where's tau max? Is tau max? I'm going to sketch tau max now over here. Okay, so this is where our tau max is. Okay, what I'm drawing now on mole circle. Over here, this is our tau max. We have to determine this value. Okay, so what we have is we know that our shear is 158.519 omega L. Okay, that is our shear stress on the element. And the normal stress, we also have our normal stress, and our normal stress is what? 141.579 omega L squared. So this point over here is equal to minus 141.579 omega L squared. So now we have to determine tau max. Okay, so there's a line over here which I'm going to sketch, and this line is known as our stress average line. Okay, so the distance from here to here, from 0 to where the green line is, which is our center of the circle, this is our stress average, and this point over here is not, is the center of the biggest circle. So from here, we are going to determine what is our stress average. Okay, so stress average is really straightforward when we learn mole circle. So stress average will be equal to normal stress X plus by normal stress Y divided by 2. Okay, so stress X is minus 141.579 omega L squared divided by 2. And this will be equal to 141 minus 70.79 and minus 70.79 and is omega L squared. Okay, so why do we have to determine our stress average? Is because after knowing our stress average, and we also know the distance from here to here, we know that this height, okay, this height is 158, right? This is our shear stress height. So from here we can determine the radius. Okay, we can determine the radius, and the radius is the tau max. Okay, the radius of the biggest circle is tau max. So therefore, radius of the circle which is equal to our maximum shear stress, it will be equal to, so all we need to do now is we know the stress average from 0 to here, we know the stress average, so it's 70. Because we are going to square them, you can drop the negative omega L squared, the whole thing squared, then plus, and then the shear is 158.519 omega L, and the whole thing is squared. Okay, so the tau max equation now, just so we know, the tau max is 17.79 omega L squared, the whole thing squared, plus by 158.519 omega L squared. So we know that based on the maximum shear stress criteria, right? We know that tau max will be equal to 100 times 10 to the power 6 Pascal, right? Written down here on our previous page, right? We know that this is equal to stress U divide by 2. In fact, I will not skip step. So basically, this is equal to 200 times 10 to the power 6 divided by 2. So this is equal to 100 times 10 to the power 6 Pascal. So from here, we can form this equation. So we will have, so I'm going to drop the square root and I'm going to bring over the other side. So we have, I'll write the whole thing down. Okay. So what we have now is 70.79 omega L squared, the whole thing squared, plus by 158.519 omega L squared. And over there, the whole thing will be equal to 100 times 10 to the power 6. So if we're going to drop or we're going to remove the square root,